Sample 6-5, a turn on a level road. This is a fairly easy problem once we get over the question of what's providing the centripetal force. So we have a car of mass M exits the freeway and travels around a circular off-ramp at a constant speed of 15.7 meters per second. They give you a couple other speeds. Don't worry about those. You wanted meters per second anyways, but miles per hour probably gives you the best gauge for how fast the car is actually going. The ramp is level and not banked. You can thank me later after we do the turn on the banked road. So the centripetal force has to be provided by the friction between the tires and the road. If the coefficient of static friction is given, we're going to find out what safe radius of curvature is needed. Okay, how big does this off-ramp need to be? So we're told that the car is going to take this at a rate of 15.7 meters per second, and we're told that the coefficient of static friction between the tires and the road is 0.550. And we'll talk in a minute for why that's static friction and not kinetic friction, even though the car is moving. So again, it's sometimes helpful to look in your book for these circular problems. We're on page 241. And the car is again on the right-hand side of the turn. So the free body diagram for the car is going to look like this. The weight of the car is going to act down. The normal force is going to act up. Those should be equal. They don't look very good. In this scenario, the car is actually coming towards us. Friction is keeping it moving in a circle. And so that is going to be, I'm going to call that Fs. Okay. And that friction acts towards the center of the circle. Okay, now since friction is acting as a force keeping this car in a circle, it's a centripetal force, and we can use mv squared over r to solve for whatever we need to solve for. So again, static friction is acting as a centripetal force here. It's not kinetic friction because when you think about what makes a car go, it's actually static grip between the tread of the tire and the road. So think about trying to walk on the ice. You need static friction. You don't need kinetic friction. And the reason it's hard to walk on the ice is because there's not much static friction between your foot and the ice. So it is static friction that keeps an object moving in a circle like this. So if you are sitting on the outside of a merry-go-round or something like that, you will use static friction. So, but the forces are calculated the same. And just like in chapter or in unit 2, Fs max is still equal to mu s times the normal force. And in this scenario, when there's no other y forces around, okay, this can be different when the road is banked, next sample, but the normal force is just equal to mg, okay? So what's holding the car in a circle? Fs max is a centripetal force. So we can say that's equal to mv squared over r, right? Now substituting this in for Fs max, we have mu s times mg equals mv squared over r. And doing some manipulating with your algebra, you get a radius of 45.7 meters, okay? Now, when you're exiting the freeway or going around any circular path and you see that speed limit, it'll say, suggest that you take this off ramp at a speed which is much lower than your highway speeds. You'll notice that it doesn't say, oh, little cars go at this speed, but bigger cars, you have to go slower, or bigger cars, you can go faster. And as you might not be surprised at this point, the mass does cancel out of this. So what really matters is the speed of the car, how big the radius is, and then how grippy is that road. Obviously, maybe not obviously, when it's rainy and the roads are slipperier, this goes way down. So the safe speed at which you can take these turns also goes way down. So if your parents have ever nagged you about driving too fast in the rain, this is why that coefficient of friction between your tires and the road goes down significantly. And you can see that from the expression. So that's how we figure out the radius of the turn here. And this is what city planners and civil engineers do all the time when they're designing off-ramps and roads and things like that. You have to know the coefficients of friction of various materials and the tires that are driving on it. And that's how you kind of back out the speed. So we kind of did this a little bit backwards. I would rather have started with the radius of the turn and determine the speed, but we're going to save that for the next example, which is a turn on a banked road. So take a look at this until it makes sense. You don't want to go on to the banked road until the level road makes sense, because it gets disproportionately more difficult. But if you have questions on any of this, let me know.